If we have a car that's sitting at the top of a hill, about to roll down the hill, we want to find the speed of that car at the bottom of the hill, we would use conservation of energy. The energy at the top of the hill is equal to the energy at the bottom of the hill, or EI is equal to EF. The law of conservation of energy says that the total energy remains constant, so EI will be equal to EF. We just have to determine what kind of energy we have at the top and the bottom. If we have a charged particle that's about to go across a gap between two parallel plates or some potential difference, and if it speeds up as it goes across the gap, we're going to treat that the same way. Once again, we're going to say EI is equal to EF, the law of conservation of energy. The total initial energy equals the total final energy. In both cases, what kind of energy do we start with? Potential energy, right. Now, because we start with potential, by the way, in both cases, that potential energy ends up changing into what? Kinetic at the bottom. So in both cases, we end up losing or converting potential energy. We end up gaining kinetic energy. Potential energy is converted to kinetic energy. The only difference here is that this potential energy is mgh, this potential energy is qv. This kinetic energy is 1/2 mv squared, so is this one. Because kinetic energy isn't dependent upon type or scale or whatever. A charged particle accelerating has the same kinetic energy as a car that's accelerating down a hill. What doesn't change? The total energy. The total initial equals the total final, regardless of whether you're talking about a car speeding up or a charged particle speeding up. Listen, we talked about this yesterday. Whenever a charged particle speeds up, whenever a charged particle accelerates, I want you to think of it as a car going down a hill. Why? Because we can see this. We can visualize the car going down a hill. We can see the color of the car. We can visualize when it has potential energy. We can visualize when it has kinetic energy. It's a little bit harder to do with a charged particle that's accelerating. So visualize it, picture it as the car, fill in the equations as if it was a car, and then just replace mgh with qv wherever you see it. We had a question yesterday. We did it yesterday in class. It's question 1A, example question 1A. We wanted to find the speed of the electron when it went halfway across a set of parallel plates. This electron was speeding up. It was accelerating. That's like a car going down a hill, right? What kind of energy would a car at the top of the hill start with? Potential energy, right? It has to have potential energy, otherwise it's not going to go down the hill. So it would start off with potential energy. This one was moving at the top of the hill as well. So Tim, if the car was moving at the top of the hill, it would also have what? Yep, kinetic energy at the top of the hill as well. What kind of energy does the car have when it's made it halfway down the hill? Both. It's still got a height, so it's still got potential energy, mgh, and it's now moving a little bit faster than it was before. It's got kinetic energy as well. Now, what you got to do, of course, is replace mgh with qv. And sub in your numbers and solve for the final speed. It's exactly the same thing in terms of thought process as the car going down a hill. We just have to replace mgh with qv. Sub in our numbers and do what we do. You had one question that I asked you to work on last night. It was worksheet number 9, question number 1. The question says, an electron is accelerated from rest across a potential difference of 85 volts. What's the final speed of the electron? What's happening to this electron? Speeding up, slowing down? Mateo, you weren't here yesterday, but you could tell me what happens here. Is this electron speeding up or is it slowing down? The electron is accelerated from rest to some speed. Speeding up. If you can picture a car at the top of a hill rolling down the hill, the car speeds up, right? What kind of energy would the car have at the top of the hill? Picturing a car right now, right? What kind of energy does the car have at the top of the hill? Potential energy, right? It would be mgh if it was a car, and that's the way we're visualizing it. Janae, does it have kinetic energy at the top of the hill? Right, it says it starts from rest, right? If it was moving at the top of the hill, it would also have kinetic. We're just going to say MGH equals, what kind does it have at the bottom of the hill? Kinetic because it's moving, right? Does it have potential at the bottom of the hill? No, because there's no height now. Now, we're going to replace MGH with QV because it's not gravitational potential energy that it has, it's electric potential. But we're just picturing it as gravity because it's easier to picture. 700 numbers here now. 1.6 times 10 to the minus 19 times 85 volts equals 1/2 of 9.11 times 10 to the minus 31 times VF squared. By the way, this is technically potential difference delta V, not VI. But if the final potential is 0, and we've assumed that the final potential is 0, right? Nick told me, I think, was it you that told me that the potential energy at the end is 0? Somebody told me that the potential was 0. If there is no potential at the end, the final potential is 0, then even though technically they're giving us not the initial potential, they're giving us the potential difference, isn't that the same as the initial potential? The difference will be the same as the initial if the final is 0. That's always going to be the way it ends up being. Solve for VF there. Okay, it works out to be 5.46 times 10 to the 6 meters per second. Is that okay? Okay, I'd like you to take a look at questions 2 and 3. We'll give you about 5 to 7 minutes to work on those questions. Then we'll take a look at one of them, and then we'll move on with one more example, and that'll be it for us. Number 3 says an electron is accelerated through a potential difference of 9 volts. The electron begins at a speed of 6 times 10 to the 4. What's the final speed of the electron? This electron is speeding up, right? If it's speeding up, that's like a car doing what? Going down a hill, yeah. And when a car goes down a hill, we say EI is equal to EF. So let's set it up that way. And then let's ask ourselves the question, what kind of energy does this car have at the top of the hill? This car at the top of the hill must have what kind of energy? Always has potential energy at the top of the hill, right? So we'll say MGH for a car, remember? In this case, there's also kinetic energy at the beginning because it's moving. It starts off at a speed of 6 times 10 to the 4 meters per second. Now, what kind of energy does it have at the end of this problem, after it's accelerated, at the bottom of the hill? Ben? Kinetic energy, good. So we're going to say 1/2 mv squared. Now, we're going to replace MGH with QV, right? We don't want MGH in there. You know what? Most of you guys are probably going to just not even write the MGH. Okay, most of you guys are going to probably write it directly as QV, and that's fine. But we still want you to visualize it as a car going down a hill, because again, we can see that. If you want to skip the step of writing in MGH and then erasing it, that's okay, but we still want you to visualize it that way. All right, we sub our numbers in here now. Q is 1.6 times 10 to the minus 19 coulombs. It's actually negative, but we always drop the sign of a charge in an equation. The initial potential is 9 volts. Really, that's the potential difference. But since the final is 0, the initial is the same as the difference. The mass of the electron times the initial speed, 6 times 10 to the 4. Don't forget to square it. Oh yeah, lots of numbers here that we got to work through. We're going to say, here, let's bring this over here. On the left-hand side, we're going to say 1.6 times 10 to the minus 19 times 9. There's the first term. 1.44 times 10 to the negative 18. Let's add to that now. 0.5 times 9.11 times 10 to the minus 31 times 6 times 10 to the 4 squared. Okay, there's the whole left side now. I've combined the first term and the second term. Now, let's take the half over by multiplying by 2. Let's take the 9.11 over by dividing by that value. And we're not quite done, but now what do we got to do? Square root it. We end up getting a value of 1.78 times 10 to the 6 meters per second. So we were going 10 to the 4, now we're going 10 to the 6. Does that seem reasonable? We sped up, right? Makes sense. See, charged particles speeding up. It's now going 10 to the 6 meters per second. Good. I got one more example for you here. This one says an electron is released in an electric field, and it's moving at 5 times 10 to the 6 in the direction of the field. Draw this out to see what's going on, okay? Here's the electric field direction. To the right, we'll say. It doesn't really matter which way. It's to the right. We have an electron that's moving to the right. Which way is the force on that electron? Down? No. To the left. If it's a positive particle, the force is with the field. If it's a negative particle, the force is against the field. So the force is to the left here. If it's moving to the right, but the force is to the left, what's going to happen to this thing? What's going to happen, Ben? Yeah, it's going to slow down. If it slows down, that's like a car going up a hill, right? So let's picture this as a car going up a hill now and identify what kind of energy the car has at the bottom of the hill. It has kinetic. It's got to be moving, otherwise it's not going to go up the hill. Now, it says determine the potential difference required to stop the electron. If the electron stops, the car stops when it gets to the top of the hill. What kind of energy does it have when it gets up there? Potential. There's no kinetic if it stops, right? Potential. Except we're going to replace MGH potential with QV potential. Don't get that mixed up with QE. That would be electric force. QV is electric potential energy. So we sub some numbers in here now. Now we're solving for VF, final potential. We're looking for the potential difference, but if the initial potential is 0, then what's the final potential? If the initial is 0, then the final potential is the same as the change, right? The potential difference. So once again, we're just really looking for VF here. When we do this, half times 9.11 times 5 squared divided by 1.6 gives us 71.2 volts.